with that, I am truly delighted to introduce the next performer to the stage, Dr. Athena Stein, here in the School of Medicine, been championing the development of novel, non-invasive brain stimulation treatments, non-pharmacological, safe and effective treatment for psychiatric disorders such as depression and anxiety by learning how to speak the language of the brain. The language you see right here as part of that conversation. As I had the delight to find out, Dr. Stein is not only an accomplished star in the field of non-invasive brain stimulation, also she has many other talents that she will share today with you. Thank you very much. Please, Athena, to the stage.
Every brain has its own soundtrack. And in mental illness, that soundtrack can get disrupted. Rhythms can speed up, slow down, or fall out of sync. In order to make a healthy soundtrack, all the different parts of the brain need to work together in a coordinated way. Just like the different parts of the saxophone work together to make music. Let me show you. My name is Dr. Athena Stein, and I'm a neuroscientist at the Carolina Center for Neurostimulation here at UNC's Department of Psychiatry. My work focuses on developing new non-pharmacological treatments for mental illness. In particular, creating new non-invasive brain stimulation technologies for the treatment of depression and anxiety. In my past life, I was trained as a classical saxophonist and saxophone teacher almost a decade ago now. And recently I picked up my saxophone for the first time in a long time to bring the two worlds back together and talk about the saxophone as a metaphor for the brain. So you can think of the parts of the saxophone as the brain's structure. We have the mouthpiece, the neck, the body, and the bell, and the sound that it produces as the brain's function, the patterns of activity that make you, you. In psychiatry, we know that when the structure or the connectivity is disrupted, the function changes too. So let's change the structure of the saxophone and see what happens to the function. We start with the mouthpiece, the most basic part of the saxophone. The mouthpiece is where the sound starts, and on its own, it makes a pretty basic sound. Not that nice, right? The mouthpiece is like the brainstem, the most primitive part of the brain that connects the brain to the spinal cord and is responsible for autonomic functions like breathing, heart rate, swallowing. Then we can connect the neck, and now we have a relay between the mouthpiece and the rest of the saxophone. This is like the thalamus. The thalamus is the relay station between the deeper parts of the brain and the cortex, which coordinates complexity and control. And now we have a slightly more complex sound. So now we can add the mouthpiece and the neck to the rest of the saxophone, and now we have complexity, control, and coordination, like the cortex. So now I want to talk about what happens when the brain's structure gets disrupted. For example, in brain injuries or in neurodegenerative diseases. If there is a small amount of structural disruption, the brain can often compensate and rewire, create new pathways to achieve the same amount of function. So we can model that with the saxophone. On saxophone, we have a note, B flat. It sounds like this. And I can play B flat in 3 structurally completely different ways with 3 different key configurations to get the same note. I can play it like this, or like this. 3 completely different ways to get to the same function. However, if there is too much structural disruption in the brain, for example, in maybe moderate to severe brain injuries or later stage neurodegenerative disease, the brain can not always compensate to achieve the same function. So we can model that on the saxophone as well, and I need a volunteer for about 20 seconds for this. Can I grab someone? Sorry. Can you please hold down this and this? So just put your finger there and there. And I'm going to play that same C major scale as before. Thank you.
Welcome.
So, as you heard, it didn't sound very good, and I saw Ellie's brain waves change there actually too a little bit. They're back to normal now. It didn't sound very good. I changed the structure of the saxophone too much, and the function couldn't compensate. So now I want to talk about rhythms. Your brain runs on rhythms, or oscillations. And these oscillations are how the different parts of the brain coordinate with each other and with the outside world. And we know in mental health disorders, these rhythms get disrupted. So in our lab, we study these rhythms as biomarkers for mental health illnesses and specific symptoms of these illnesses. And once we understand the biomarker, we're then able to target it using non-invasive brain stimulation. So the way that the brain stimulation works is we deliver very small rhythmic electrical currents to the brain while participants are just relaxing, watching a video through a couple of pads on their forehead. And that small amount of electricity can actually cause the participant's brain activity to lock onto our rhythm, so we can subtly nudge rhythms back into place. So we can actually model that together. I'm going to play a little rhythm on my saxophone, and I would like you all to clap along, and I'll help you. All right. Awesome. So I entrained you. I locked you to my rhythm. And that's exactly what we do with brain stimulation with the brain. However, it's really important that the stimulation that we apply is something that is understandable by people's brains, because if it's too different, we aren't able to entrain the brain activity. So we're going to try that exercise again. I would like you to clap along, and I'm going to do something slightly different. All right, ready? Okay, we fell out of sync. I changed the rhythm unpredictably in a way that you weren't expecting or weren't used to, and that's also a really important concept in brain stimulation. The input that we give the brain needs to be understandable by the brain. So in our lab, we work to personalize brain stimulation to be understandable for each person's brain, because if we can better speak the language of the brain, then we can better engage those targets. So bringing this all together, I want to finish with showing you what happens when brain structure and function comes together to make music. And this is a small piece of the Glazunov saxophone concerto.
And now you are neuroscientists too. That principle of rhythmic engagement that you yet experience in a different way, the different frequencies, the meaning behind the rhythms as a target for healing. I fundamentally believe that this is the common pathway of experiencing ourself, our connection with the world and the world, the alignment of our own inner physiology with the world around us. The healing power of music has only recently started to be part of a scientific inquiry, yet culturally and historically, music brings together, music connects, and it's that connection that heals.